Vanakkam நேயர்களே. Dear students, now we are really passing on to the another very important area. Already you might have seen the two important PPTs. Number one, we have given you the three-dimensional view of the particular chapter. The Siksha video we have displayed might have already covered the complete chapter NCERT chapter vertically in three-dimensional view. Now, we are really interested in deducing the formulas and the concept from the particular chapter, and we want to identify the problem areas and want to do the problems types also for your perusal here. This is the second important exercises we are really interested in doing. The third one is, we are really going to solve the NCERT problems and exemplar problems. These three exercises will ultimately cover the whole topic. May we pass on? So, solids, properties of solids, stress, mono type of stress. Strain, mono type of strain. Modulus, mono type of modulus. In the mono type of stress, strain, modulus problem போட்டுட்டு concept தெரிஞ்சுக்கிட்டோம் அப்படினாக்க போதும். Now we'll be passing on to the concept of the problem solving.
Okay, welcome to iLecture Online. In this next set of videos, we're going to talk about the stress and strain of materials. And we're going to start out with the very basic concept of what that really means. So first of all, we're going to define the term stress. Stress on a material is simply the force divided by the cross-sectional area over which it is applied. For example, if you have a beam like this and you push down on it with a certain amount of force and the beam has a certain amount of cross-sectional area, the stress is simply expressed in terms of the ratio of the force divided by the area. Now notice that if we have a larger cross-sectional area, like a much bigger beam like that, and we apply the same force, but the area is different, then the material will experience a different amount of stress. And you can see that if the area is larger, a larger area makes this a smaller quantity, that means there is less stress. So this beam is experiencing less stress than this beam, even though the amount of force applied to the beam is exactly the same. So you can see how stress is actually a function of both the force applied and the cross-sectional area of the material. So here we can see that there's a large amount of stress applied to this material, this beam right here, and here is a smaller amount of stress applied to the beam. The second part of the relationship between stress and strain is the second portion, namely strain. And the definition of strain is that it's a ratio of how much the material deforms, so let's call that deformation. In the case of a linear element here, like a linear beam, if we push down on the beam, we may make the beam a little shorter. We're deforming it by making it shorter, and that's called deformation. And if we find the amount by which it deforms divided by the original size of the object, so for example, this may be the deformation, the reduction in the length of the beam after we apply a certain amount of force on it. So let's assume we apply a force, and therefore because of the force applied, we actually make the beam shorter. So we deform the beam, and the ratio of the amount of the deformation divided by the original shape, which would be in this case the original length, is what we call the strain. In this case, if the deformation is large, we expect a large strain. In other cases, the beam may only, under maybe applying the same amount of force, may not experience the same amount of deformation. In this case, the deformation is relatively small, so therefore, the ratio of the deformation divided by the original length is much smaller, and so therefore we can say that there's a small amount of strain on this beam and a large amount of strain on that beam. So why would that be? Why would some beams have a large strain when a certain amount of force is applied, and other beams will have a very small strain? Well, that has to do with the strength of the material of the beam. And so let's imagine, for example, that this is a beam made out of steel. And of course, if we take a look at the molecular level, if we zoom in to a very small portion on the beam, and we take a look with a very powerful microscope, and we see that this beam is made up of atoms, And those atoms are usually, in a solid object of course, in a crystalline structure of some sort. They're usually locked into a certain structure. They do vibrate because of the thermal agitation, but they're all locked into one another. And the atoms are spaced just exactly right so that the forces between them is balanced out, and so they take up a certain amount of space between them, and they have a certain amount of space between each atom. So now what happens when you apply a force on a beam like that? Well, what you're trying to do is you're trying to push the molecules closer together. Now, if the molecules can easily be forced closer together, then you'll experience a large amount of strain. If the molecules experience a lot of force so that there's not a lot of room for them to be compressed together, then you experience a much smaller strain. For example, metals tend to be of the type where you have very, very small amount of deformation. You take a steel beam, you try to push on it, you're not going to make it much smaller. But if you take, for example, a beam made out of foam and you push down it, you'll see that there's a lot of strain because the molecules do not, they're not very cohesive. There's not a lot of as much force between them to hold them in shape. So that's where you find a different amount of strain. Now what we tend to do with this, the concept of stress and strain, and by the way, one more thing I wanted to point out, notice that stress is force divided by area, and that would be newtons per square meter, and that is also those are also the units of pressure. So it turns out that stress is very synonymous with pressure, and so again, pressure is force per unit area. Large amount of force, small area, a lot of pressure. Small amount of force, large area, small amount of pressure. So there's a lot of similarity between pressure and stress. Now, if we find the ratio between stress and strain, so we take stress, which is force divided by area, and divide it by the strain, that ratio gives us an indication of what kind of material we're dealing with. For example, if we apply a small amount of, let's say we apply a large amount of stress, and there's a small amount of strain. In other words, just a little bit of deformation when we really push down on the material. If that ratio is large, what kind of material are we dealing with? We're dealing with a very strong material, a material that it does not deform very easily. And so this then would indicate a certain amount of property relative to the material, and we'll talk about what that is in just a moment. On the other hand, let's say we apply not a lot of stress, not a lot of force, and the strain is considerable so that this fraction is large, so that fraction is small, because that's what it says right here. So again, small amount of stress, a considerable amount of strain, so the ratio is very small, and we're dealing with a very weak material, a material that very easily compresses. So here we're dealing with a weak material. Now, since this ratio of stress divided by the strain, again, stress is kind of like pressure, how much force we apply to it per unit area, and we divide that by the strain, how much deformation is relative to the original shape of the object. When we take that ratio, if that ratio is large, we're dealing with a strong material. If that ratio is small, we're dealing with a weak material. And so it turns out that we call this ratio something. We call that the Young's modulus. So the Young's modulus is an indication of how strong or how weak the material is. And strong or weak, we're talking about in terms of how much it can resist deformation under stress. And so, again, we're going to talk about Young's material in a future video, in a few videos down the road, a little bit more after we get the basics out of the way. But again, notice that that ratio does give us a property of the material, and so we'll talk a little bit more about that later. But here you have your basic concept of stress and strain and how that ratio actually means something to us, and we'll take use of that in future videos.
தமிழ் மீடியம் மாணவர்களுக்காக சொல்றோம். ஃபோர்ஸ் பை ஏரியா, விசை பை பரப்பு அப்படின்றது தகைவுன்னு சொல்றோம். பரும மாறுபாடு பை ஆரம்ப பருமன் என்பது ஸ்ட்ரெயின். இந்த ஸ்ட்ரெஸ்ஸுக்கும் ஸ்ட்ரெயினுக்கும் உள்ள ரேஷியோக்கு பேரு யங்ஸ் மாடுலஸ்ன்னு பேர். இப்போ ஒரே விதமான டிஃபார்மிங் ஃபோர்ஸஸ் ரெண்டு பாடி மேல ஆக்ட் பண்ணுது. ஒரு பாடியினுடைய பரப்பு கம்மி, இன்னொரு பாடியினுடைய பரப்பு கூட அப்படின்னாக்க ஸ்ட்ரெஸ் மாறுபடுது. கூடுதலான பரப்புல ஒரே ஃபோர்ஸ்னால வரக்கூடிய ஸ்ட்ரெஸ் ஃபோர்ஸ் அதேதான், ஏரியா கூட, அப்ப ஸ்ட்ரெஸ் கம்மி. ஏரியா கம்மி, ஃபோர்ஸ் அதே தான், ஸ்ட்ரெஸ் கூட. ஸ்ட்ரெஸ் மாதிரியே தான் ப்ரெஷருக்கான யூனிட்டும். ஸ்ட்ரெஸ்ஸும் ப்ரெஷரும் ஒண்ணுக்கு ஒண்ணு இயைபான சமன்பாடுகளை கொண்டது. தகைவு அப்படின்றது ஃபோர்ஸ் பை ஏரியா, அழுத்தம்ன்றதும் ஃபோர்ஸ் பை ஏரியா. ஆனா ஒரே ஒரு சின்ன வித்தியாசம், ப்ரெஷர்ன்றது எக்ஸ்டர்னல், இந்த ஸ்ட்ரெஸ்ன்றது இன்டர்னல். அதே மாதிரிதான் ஸ்ட்ரெயினும். இப்ப பாருங்களேன், ஒரு பாடி மேல ஒரு ஃபோர்ஸ் ஆக்ட் ஆகி அந்த பாடியினுடைய நீளம் குறையுதுன்னு வச்சுக்கலாம், கம்ப்ரசிபிள் ஸ்ட்ரெஸ். இப்ப இந்த நீளம் அதே ஃபோர்ஸுக்கு அதிகமா குறையுது, அதே ஃபோர்ஸுக்கு குறைவா குறையுது. உதாரணம், ரெண்டாவது கேஸ் ஸ்டீல் ராடு, முதல் கேஸ் ஃபோம் ராடுன்னு வச்சுக்கோங்க. ஃபோம், ரப்பர்னாலான ஃபோம். இப்போ எதுக்கு யங்ஸ் மாடுலஸ் அதிகம் அப்படின்னாக்க, நல்லா கவனிச்சிங்கன்னாக்க, அதிகமான ஸ்ட்ரெஸ்ஸுக்கு குறைவான ஸ்ட்ரெயின் இருந்தா அந்த மெட்டீரியல் ஸ்ட்ராங்கா இருக்கும், ஸ்டீல் ஸ்ட்ராங்கா இருக்கும். இங்க ஃபோம் அதே ஸ்ட்ரெஸ்ஸுக்கு அதிகமான ஸ்ட்ரெயின் இருக்கு, டினாமினேட்டர் கூடியிருது. அதனால யங்ஸ் மாடுலஸ் குறைவா இருக்கு. வீக் மெட்டீரியல் ஃபோமையும் ஸ்டீலையும் கம்பேர் பண்ணா அதே ஃபோர்ஸுக்கு மிக அதிகமான ஸ்ட்ரெயினை உருவாக்குறது ஃபோம், குறைவான ஸ்ட்ரெயினை உருவாக்குறது தான் ஸ்டீல். ஆனா யங்ஸ் மாடுலஸ் எதுக்கு கூட, ஸ்டீலுக்கு கூட, ஃபோமுக்கு கம்மி. இப்ப முதல் கான்செப்டை வலியுறுத்தி இருக்கோம். அடுத்து போலாம்.
In our lecture online, and in this next video we're going to explore stress and strain a little bit more. In this case we're going to talk about what we call either tensile or compressive stress and strain. So in this case here we have a bar and we're pushing on the bar from both ends, trying to make the bar shorter. In this case we say that the bar is under compression. We're trying to compress the bar, we're trying to make the bar shorter. And so therefore when we talk about stress, we really talk about compressive stress. And again, it's the force applied on both ends. Of course, Newton's third law requires us to push with an equal amount of force on both ends. So we take the force on either end and divide it by the cross-sectional area, and that would then be the stress. Again, the stress is determined both by how much force you apply and over how big a cross-sectional area you apply it. The strain then is the deformation divided by the original size. In this case, this will be in terms of length. And so by compressing the bar, we're making the bar a little bit shorter. That's delta L. Notice when we make it shorter, we tend to use a negative because it's decreasing in length. And that would then be the original length. So that would be the ratio of the change in length over the original length, which is called the strain. And again, the ratio of the stress over the strain, when we write it like this, is F over A divided by the change in the length divided by the original length. And we can ignore the negative for a moment. Just that ratio by itself is called the Young's modulus. Now, let's take a look at our second bar. In this case, we're pulling on the bar, both ends, and pulling apart from each other. Again, those forces have to be equal, Newton's third law, because if one was bigger than the other, the bar would accelerate in one direction or in the other direction. So for the bar to stay stationary, you got to pull both directions with the same amount of force. We now say that the bar is under tension. We're pulling on the bar, we're trying to make it longer. That's called tension. And therefore, instead of calling it compressive stress, we're going to now call it tensile stress, since we're pulling on it, the bar is under tension. So tensile stress is defined exactly the same way. It's force divided by area. And the tensile strain is the deformation, in this case the length, divided by the original length. Notice here it will be a little bit longer, so delta L is therefore positive. And if we find the ratio of that, stress over strain, it doesn't matter if it's compressive stress and strain or tensile stress and strain, the ratio means exactly the same thing and still will be the Young's modulus. The vast majority of materials, if not just about all materials, they have the same ratio of stress over strain regardless if you compress it or if you stress it in the opposite direction. So compressing or put under tensile stress, you find the same ratio. So again, to illustrate that ratio, we call that Young's modulus, and we'll talk a little bit more about that in a later video. But again, understand that the size of this ratio talks about, or the size of the ratio implies the strength of the material. How easily does it resist deformation? The bigger the number, the bigger the ratio, the more it resists deformation. The smaller the number, the less it resists deformation. So as an example, we have two materials, call it aluminum and call it brass. Aluminum here has a Young's modulus of 7 times 10 to the 10th newtons per square meter. Brass has a Young's modulus of 9 times 10 to the 10th newtons per square meter. So without going into the details, because we'll do that in the next video, a couple videos from now, we just want to look at those numbers, and can you tell from looking at these numbers which material resists deformation the best? And since brass has a larger Young's modulus, you could say brass resists deformation better than aluminum. So putting the same amount of force on brass and aluminum, aluminum will deform a little bit more, brass will deform a little bit less. As long as the force are the same and of course the length is the same. If the length is different, of course, then of course again, the ratio will still take care of itself. But I would say what's important is that we look at the compressive stress and that the force divided by the area is similar or the same for both, otherwise you can't compare them very well. But again, the ratio of the stress over the strain, you can see the result. Aluminum, not so good. Brass, a little bit better. But even though aluminum has a smaller number, that's still a really big number, and you can see you need a lot of force to cause any sort of appreciable deformation, even if it's aluminum. But that's just for comparison. And that's how you look at tensile stress and compressive stress.
அப்போ ஸ்ட்ரெஸ் ரெண்டா பிரிக்கிறோம். டென்சைல் ஸ்ட்ரெஸ்னு ஒன்று பிரிக்கிறோம். பிறகு கம்ப்ரசிவ் ஸ்ட்ரெஸ்னு ஒன்று பிரிக்கிறோம். விசையினால நீளம் குறைஞ்சா கம்ப்ரசிவ் ஸ்ட்ரெஸ், விசையினால நீளம் அதிகரிச்ச டென்சைல் ஸ்ட்ரெஸ். அதாவது நீள மாறுபாடு அப்படின்றது கம்ப்ரஷன்னால குறையும், ஸ்ட்ரெஸ்னால இன்க்ரீஸ் ஆகும். இதை வச்சு 2 ஸ்ட்ரெஸ் போட்டிருக்கோம். ஆனாலும் இதனால கிடைக்கக்கூடிய யங்ஸ் மாடுலஸ் ஒண்ணுதான். 2 மெட்டீரியலுடைய யங்ஸ் மாடுலஸ் இங்க கம்பேர் பண்றோம். அலுமினியம், பிராஸ் நம்பர் அதிகமா இருந்ததுன்னா அந்த மெட்டீரியல் ஸ்ட்ரென்தர் மெட்டீரியல் அப்படின்னு சொல்லப்படும். 70 அது 7, 9 அலுமினியத்தை காலத்திலும் பிராஸினுடைய யங்ஸ் மாடுலஸ் அதிகம். அதனால பிராஸினுடைய ஸ்ட்ரென்த் அலுமினியத்தை காட்டிலும் கூட. இப்போ இந்த டென்சைல் ஸ்ட்ரெஸ் வச்சுக்கிட்டு நம்ம நடைமுறை வாழ்க்கையில ஒரு அப்ளிகேஷனை பார்க்கலாம். ஐ பீம்னு சொல்றோம். ஏன் அந்த பீம் ஐ வடிவத்தில் இருக்கு அப்படின்றத இங்க எக்ஸ்பிளைன் பண்றாரு.
Here we're going to see a very interesting application of tensile strength and compressive strength, and tensile stress and compressive stress. So going back to the concept, here we have a beam. Let's say the beam is suspended at both ends, and beams are usually used to hold big loads so that we could put forces on them. And so let's say we apply a force to the beam, and if the force is very large, typically the beam will be, as a response, will begin to sag to some extent. Of course, I exaggerated the sag so we can see what happens, but what the result is that the atoms near the top of the beam get pushed together, and so there is a compression taking place near the top of the beam. On the other hand, on the far end of the beam, from where the force applies at the bottom end of the beam, the belly of the beam, so to speak, that part of the beam is under tension, meaning the molecules are being pulled apart. And of course, the danger is that if you apply too much force, the beam could actually begin to crack. So for example, you have a wooden beam, you apply too much force, you can actually destroy the beam. And of course, that's the purpose of the beam, is to hold a lot of weight. But if the beam starts cracking, of course, it doesn't do what it's supposed to do. So what people started realizing is that, wow, what's really the part of the beam that's really under compression and under the most compression is the top portion of the beam right here. So what I did over here is just kind of mark that off. It's this portion of the beam that's going to be under the most compression. The most force is applied to the beam, pushing the molecules together. And the bottom end of the beam is going to be under the most tension. Because of the sag of the beam, the molecules are going to be pulled apart the most at the very bottom of the beam. So those are the 2 portions of the beam that are the most important, and the portion in the middle is not near as important for the strength of the beam. So therefore, we build what we call the I-beam. Beams that have a very wide section at the top, which is not necessarily very thick, but very wide. Then we have a single, very thin portion going down, and then we have a second portion right here, which is the bottom end, again, that is very wide, not necessarily very thick. And so what happens then is that portion now, as you put force on the beam, and you can put a lot of force on the beam right here, then this is going to be again under compression. As the beam sags, those molecules are going to be pushed together. But since there's such a large cross-sectional area, that causes, therefore, the ability to absorb a lot of force. So the stress will be reduced simply by the fact they have a much larger cross-sectional area here than you do over there in that part of the beam. And then likewise at the bottom of the beam, by pushing down on it, those will be under tension. Those molecules are going to be pulled apart. But again, since there's a much larger cross-sectional area, the stress will be reduced because the A is much bigger than that. So we have a much smaller stress on an I-beam compared to a typical beam like that that's built like a normal beam. Now, also, this portion, the wider you make this, it has some benefits as well. But the key areas of defense against stress from putting weight on a beam are the top and the bottom portions. So what that means is if you reduce the stress, that will then cause to have less strain as well, because the ratio of these two will always equal to what we call Young's modulus, which is dependent on the property of the material. So if we make a steel beam that has a very large Young's modulus, if we reduce the stress, we will then reduce the strain as well, and it will not sag as much. So if you want a very strong structure, instead of using beams that look like this, you're going to use I-beams, and you have a lot less strain, a lot less sag when you put weight on it, and a lot less opportunity for things to break, so they're much stronger, and that's why you use the I-beam. So, a nice application for stress and strain, and how we found a way to get around the problems of beams breaking if we put too much force on them.
மிக அழகாக stress strain relation ஹூக்ஸ் லா சொல்லுது. Stress is directly proportional to strain. அப்போ stress குறைச்சாக்க strain குறையணும் தானே? நல்லா கவனிங்க. Stress எப்ப குறைக்க முடியும்? ஒரு டிஃபார்மேஷன் ஃபோர்ஸ்னால ஒரு ஏரியால ஆக்ட் பண்றப்பதான் ஸ்ட்ரெஸ் உருவாது. அப்ப இந்த ஏரியாவை அதிகரிச்சுட்டா இங்க பாருங்க, ஒரு பீம் மேல சிக்ஷா வீடியோல ரொம்ப அழகா அந்த அனிமேஷன் இருக்கும். ஒரு பீம் மேல ஒரு டிஃபார்மேஷன் ஃபோர்ஸ் வந்ததுன்னா மேல் சர்ஃபேஸ்ல கம்ப்ரெஷனும் கீழ் சர்ஃபேஸ்ல எலாங்குவேஷனும் நடக்கும். கம்ப்ரெஷன் நடக்கக்கூடிய ஏரியாவை கூட்டிட்டா ஸ்ட்ரெஸ் குறையும். ஸ்ட்ரெஸ் குறைஞ்சா ஆட்டோமேட்டிக்கா என்ன குறையும்? ஸ்ட்ரெயின் குறையும். ஸ்ட்ரெஸ்ஸுக்கு கரஸ்பாண்டிங்கா ஸ்ட்ரெயின் குறையிறதுனால கீழே இருக்கிறது விரிதல் இல்லாம இருக்கு. அப்போ ஒரு திக் பீம் காட்டிலும் ஐ பீம் ஸ்ட்ராங்கர் அப்படின்னு கன்ஸ்ட்ரக்ஷனல் ப்ராசஸ்ல ஐ பீமை யூஸ் பண்றாங்க. திஸ் இஸ் அப்ளிகேஷன் ஆஃப் ஸ்ட்ரெஸ் ஸ்ட்ரெயின் ரிலேஷன்ஷிப். இதே இத இயற்கையா இப்ப ஐ பீம் நம்ம உருவாக்குனது, இயற்கையா இயற்கை உருவாக்கின எலும்புல இந்த வடிவம் இருக்கு. இது என்னன்னு பார்க்கலாம்.
And another very interesting application of tensile strength and compressive strength of materials, let's take a look at the human bones. So I'm not very good at drawing bones, but let's imagine this is maybe the femur of a human body. So how much compression can it take? Well, if you jump up and down and you come back down, there's a lot of force that pushes on those bones. So bones are made to withstand a lot of compression stress. And therefore stress, the definition of stress is force divided by cross-sectional area. So if you imagine the cross-sectional area like this of the bone, and of course the bone tends to be not solid but porous, and there's of course material inside that's like bone marrow that of course doesn't support you. But if you look at all the material that the bone is made of, and you find the effective cross-sectional area, and then you figure out how much force it needs to withstand, you can see that, of course, the human body, the bones in the human body, can withstand a lot of stress. There's not going to be a lot of deformation with a large application of force on the human body, on the bones like this. That's what bones are made for. Now, on the other hand, let's say the bone gets a force from the side. So you play a sport like soccer or something like that, and you get pushed very hard from the side where the two ends of the bone are locked in. So let's take a look at that from the side like this. A force applies on the side. Notice that the bottom end of the bone is not going to be under tensile stress, while the the top portion of the bone is going to be under compressive stress. Now, the bone is very good at withstanding compressive stress, so the top portion of the bone is in good shape, but the bottom portion, or the portion on the other side where the force occurs, that's going to be under tensile stress, so the bone molecules are being pulled apart. And bones are not nearly as strong under tension as they are under compression. And so you tend to have breaks or fractures here occurring on this side of the bone when a bone has to withstand force in that direction. So we call that a break or a fracture, and because it's caused due to stress, sometimes we also call those stress fractures, and that's where that term comes from. Now again, take a look. So we have stress divided by strain. That ratio is going to be determined by Young's modulus. So even though the deformation for bones is going to be the same, whether or not they're compressed versus elongated, the ability to withstand it is the different story. So the ability to withstand the stress, and so there's a limit to how much stress something can withstand before it begins to break. Now, for example, when it comes to compression, the stress that bones can withstand, and of course the stress is equal to divided by area, they can withstand a very large force over a very small cross-sectional area under compression. On the other hand, bones cannot withstand a lot of force when the bones are being pulled apart under tensile stress. In that case, bones will break a lot easier. The ratio of the strength of bones under compression to tensile stress is about 10 to 1, so it doesn't take nearly as much force to break a bone this way as compared to breaking a bone that way. So another nice application for tensile stress and compressive stress.
அற்புதமா கான்செப்ட் டெவலப் ஆகுது பாருங்க. கம்ப்ரெஷன் ஸ்ட்ரெஸ் அப்படின்றப்போ மேல இருந்து கீழே ஆக்ட் பண்ணுது, பாடியை குறுக்கிறதுக்கான ஃபோர்ஸ் அது பர்பெண்டிகுலரா ஆக்ட் பண்ணுது. நல்லா பாத்தீங்கன்னாக்க கம்ப்ரெஷன் ஸ்ட்ரெஸ் அப்போ போனுடைய முனைகள் இரண்டு பந்து போல அமைக்கப்பட்டிருக்கு. அங்க பரப்பு அதிகமா இருக்கு. டிஃபார்மிங் ஃபோர்ஸ் அதிகமான பரப்புல இருக்கப்ப ஸ்ட்ரெஸ் கம்மி, அதனால ஸ்ட்ரெயின் கம்மி, அதனால போனினுடைய நடுப்பகுதி மிக மிக மெல்லியதா செய்யப்பட்டிருக்கு. ஆனா தலைகளை வச்சுக்கோங்க, இந்த போன்ல கம்ப்ரசிவ் ஸ்ட்ரெஸ் இல்லாம டென்சைல் ஸ்ட்ரெஸ் வந்தா என்ன ஆகும்? 10 மடங்கு கம்ப்ரசிவ் ஸ்ட்ரெஸ் தாங்கக்கூடிய போன் 1 மடங்கு டென்சைல் ஸ்ட்ரெஸ் ஒழுங்கா தாங்காது. இந்த அமைப்புல டென்சைல் ஸ்ட்ரெஸ் காட்டிலும் 10 மடங்கு கம்ப்ரசிவ் ஸ்ட்ரெஸ் தாங்குற மாதிரி போன் வடிவமைக்கப்பட்டிருக்கு. அதனாலதான் நீங்க எவ்வளவு குதிச்சாலும் உங்க கால் தாங்குது, ஆனா சைட்ல ஒரு சின்ன அடிபட்டதுன்னா எலும்பு உடைஞ்சிருது. என்ன அழகா ஸ்ட்ரெஸ், கம்ப்ரசிவ் ஸ்ட்ரெஸ், டென்சைல் ஸ்ட்ரெஸ் இவைகளினால் உருவாக்கப்படக்கூடிய ஐபீம், போன் அப்படின்ற 2 கான்செப்ட பார்க்கிறோம். இப்போ யங்ஸ் மாடுலஸினுடைய முதல் கான்செப்ட பார்க்கலாம்.
Here we're going to take a look at Young's modulus in a more numerical fashion. So we're now actually going to do a numerical example to get a better understanding of stress and strain in Young's modulus. Again, the definition of stress. Stress is simply equal to the ratio of force divided by area. And notice the units for that would be newtons per square meter. The strain is the ratio of the amount of deformation, how much the shape of the object changes relative to its original shape. In the case of a problem where we talk about the linear dimension only, it's the change in the length divided by the original length. And notice that both the change in length and length have as units meters. Meters divided by meters, the units cancel, so there's no units. So it's meters divided by meters, which is basically unitless, right? So the strain is a unitless concept. Now, if we take the ratio of those two, stress divided by strain, notice that would be newtons per square meter or pascals divided by no units. And so we know that the ratio of that in units is simply newtons per square meter or pascals. And I use brackets to note that I'm talking about units here. And so therefore, since we know that stress divided by strain is equal to the Young's modulus then has units, newtons per square meter or pascals. And just for reference, we put down some Young's moduli numbers for various materials: aluminum, brass, copper, glass, and so forth. Notice iron is a fairly strong material. It has a very high Young's modulus. And then something like lead, which most of us have experienced, lead tends to be a very soft metal. We can deform much easier, you can see that Young's modulus for lead is much, much smaller than Young's modulus for iron or nickel or steel. All right, so now let's do our problem. We have a beam made of iron. The length originally is 1.75 meters. The cross-sectional area of the beam is 2 centimeters by 2 centimeters. And the amount of force we're applying is 1,000 newtons. 1,000 newtons, that's roughly about, let's say, about 200 pounds or so. So how much will that beam shrink in size? How much will it be deformed under that kind of force? All right, let's find out. The stress divided by strain, which by definition is equal to force divided by area, and we divide it by the change in the length over the original length, and of course that's going to be equal to what we call Young's modulus. Now what we're looking for is the change in the length right here, so we have to take this equation and solve it for delta L. Notice this gets a little messy, so I'm going to clean it up a little bit. So we're going to write as force divided by area like that, and now we're dividing that by the fraction delta L over L sub naught. So whenever we're dividing by a fraction, that's the same as multiplying by its inverse. I'm going to multiply that times the inverse of the fraction, which is L sub naught divided by delta L, and that's equal to Young's modulus. Now, to separate the delta L, I'm going to move delta L to the other side. Remember, when we have a fraction equal to a fraction, we think of this as Young's modulus over 1. We go across diagonally. So what's in the denominator on the left side goes into the numerator on the right side, and what's in the numerator on the right side goes into the denominator on the left side. So this can now be written as, and I guess I don't need the equal sign there, so we can write this as force times length initial divided by the cross-section area times Young's modulus equals delta L. So we separated out the delta L, so I can bring that over here. Delta L is equal to force times the original length divided by the cross-section area times Young's modulus. And all we have to do now is plug in the numbers. So for the force, we have 1,000 newtons. The original length, 1.75 meters. Cross-sectional area, of course, we have to convert that to meters or square meters. So we have centimeters, convert to meters, that would be 0.02 meters. And of course, we have to square that because the area of a square is a side squared. And then we divide that by Young's modulus. Since we're dealing with iron, we're going to pull out Young's modulus right there, which is 21 times 10 to the 10th pascals or newtons per square meter. In just a moment, we're going to take a look at those Young's moduli and figure out what that really means. But first, let's find the solution to this problem. So we have 1,000 newtons times 1.75 divided by 0.02 squared and divide by 21 e to the 10th equals, and that's a pretty small number. That's equal to 2.08 times 10 to the minus 5. Of course, that would be in terms of meters, because we're looking for delta L, and that would be equal to 0.0208 millimeters. And of course, if you know what a millimeter is, that's a very small distance. And so you can see that even with a force of 200 pounds, a steel beam like this, that's 2 centimeters by 2 centimeters, it's less than an inch, 2 centimeters, you would not deform the beam very much in length. It would be a very, very small deformation in the length. So how do we look at these numbers here, Young's modulus? Again, the way to look at it is the amount of stress required to obtain a certain amount of strain, a certain amount of change in the length. For example, with iron, you would need a much greater force per unit area to deform something a certain amount than you would for the same size lead. You would need a lot less force per unit area to deform it the same amount. So it's kind of a number that gives you an indication of how much force per unit area you need to apply to obtain a certain change in the length. For example, how much force would you apply if you want a 1% change in the length of the beam? Let's do that. So here we can say, let's say that we want to change the length of the beam in such a way, so what would be the force required? F is equal to question mark to obtain a 1% change in the length, so that the ratio of delta L divided by L initial is equal to 0.01, which is 1%. How much force would that require? And so not to get us too confused here, let me find a different color to work with. So what we're going to do now is we're going to find the force. We're going to put everything else over to a different location. So we're going to put the delta L over here, the A over here, the L sub naught over here. So we can say that the force is equal to Young's modulus times the area times the delta L divided by, we want L sub naught on the denominator right here. Now, realizing that delta L divided by L sub naught, by definition, is going to be 0.01. So let's plug in all these numbers. And again, let's assume we're dealing with an iron beam. Young's modulus, we have 21 times 10 to the 10th. And that would be pascals, or newtons per square meter. The cross-sectional area, okay, we know that's 0.02 meters, and we have to square that. The change in length divided by L is 0.01. Okay, so 21 e to the 10th times 0.02 squared and times 0.01 equals, and that would require 840,000 newtons. So that would be 840,000 newtons of force in order to compress the beam by 1%. So that would be 1.75 meters. So that would mean a compression of 1.75 centimeters, because centimeters is 1/100th of a meter. Wow, that would require 840,000 newtons. That's a lot of force. Another way to look at it is, notice that the units here are pascals, which are newtons per square meter. So let's assume now that we have a cross-sectional area of 1 square meter. So let's make a really big beam. So that's 1 meter by 1 meter. And we want to have a deformation of 1%. So let's say that the length of the beam, let's call it 1 meter beam, 1 meter long. And there it is. So that would be the original length. Still an iron beam, but now we have a cross-sectional area of 1 meter by 1 meter, 1 square meter. And we want the change in the length to be, again, 1%. So the delta L divided by L sub naught is equal to 1%, which is 0.01. Okay, now how much force would it take now to do that? And I think once we do that, you have a very good idea of how to look at these moduli. All right. Okay, again, we're going to take the force. So force is equal to Young's modulus times the area times delta L divided by L sub naught. But again, delta L divided by L sub naught is 1%. And notice that my cross-sectional area is now going to be 1 meter squared. So this is going to be, for iron, Young's modulus is going to be 21 times 10 to the 10th pascals, that's newtons per square meter, times 1 meter squared, times 0.01. So now that we kind of use a standard unit for cross-sectional area, 1 square meter, and we are looking for a deformation of 1% or 0.01, and that was the Young's modulus for iron, notice that then the result will be 21 times 10 to the 8 pascals. So now we have a pretty good idea that this kind of tells us the amount of force per unit area we have to apply to obtain a certain ratio of change. For example, if we want a 1% change, we multiply this by 1%, and that's the force per unit area you have to apply to gain that percent. If you want a 10% change, then you multiply, then you have 21 times 10 to the 9th newtons per square meter to deform a material. So now you can kind of see how that Young's modulus kind of plays hand in hand with the numbers you get for the force required to deform it a certain amount. Well, hopefully that'll give you some good feeling for what Young's modulus is, how we apply it, and how we can calculate the change in the length or perhaps the force required to gain a certain amount of deformation. That's Young's modulus.
மூணு கான்செப்ட் உங்க முன்னாடி கொடுத்திருக்காரு யங்ஸ் மாடுலஸ் உடைய ஃபார்முலால. ஸ்ட்ரெஸ் F by A, strain delta L by L naught. ஸ்ட்ரெஸ் பை ஸ்ட்ரெயினுக்கு பேரு யங்ஸ் மாடுலஸ். இப்போ ஒரு மெட்டீரியலுக்கு எல்லாம் கொடுத்துட்டு இந்த மெட்டீரியல்ல இந்த ஃபோர்ஸ்னால எவ்வளவு சேஞ்ச் இன் லெங்த் வரும்னு முதல்ல கால்குலேட் பண்ணார். F by A divided by delta L by L naught ல இருந்து delta L கால்குலேட் பண்ணி காமிச்சாரு. பாயிண்ட் நம்பர் 1. இப்போ சேஞ்ச் இன் லெங்த் டு ஒரிஜினல் லெங்த்ல 1% சேஞ்ச் வரணும்னா ஒரு அயன் ராட்ல எவ்வளவு டிஃபார்மேஷன் ஃபோர்ஸ் கொடுக்கணும்ன்றத கால்குலேட் பண்ணாரு. மூணாவதா என்ன செஞ்சாருன்னா ஒரு சதுர மீட்டர் பரப்பு கொண்ட ஒரு ராடுல 1% நீள மாறுபாடை ஏற்படுத்தணும்னாக்க deformation force என்ன இருக்கணும்னாக்க யங்ஸ் மாடுலஸ் into 1%. மிக எளிமையாக கான்செப்டை கொண்டு வந்திருக்காரு. அப்போ யங்ஸ் மாடுலஸுக்கான ஃபார்முலா தெரிஞ்சுக்கிட்டோம். சேஞ்ச் இன் லெங்த் அந்த ஃபார்முலால இருந்து டிடியூஸ் பண்ணி பார்த்துக்கிட்டோம். சேஞ்ச் இன் லெங்த் டு தி ஒரிஜினல் லெங்த் into 100ன்றது percentage of change. அதை எப்படி கண்டுபிடிக்கிறதுன்றத பார்த்தோம். percentage of change 1 சதுர மீட்டர்ல இருந்ததுன்னா எப்படி வரும்ன்றத பார்த்திருக்கோம். இப்படித்தான் ஃபார்முலாவை கான்செப்சுவலா மாத்தி derived ரிசல்ட்டா மாத்துறது. அடுத்து போலாம்.
Here we're going to do a very straightforward, simplistic example of how to apply Young's modulus and the concept of Young's modulus to calculate the elongation of perhaps a aluminum wire suspended maybe from the ceiling. Let's say the original length is 4 meters long, and we suspend at the bottom of the wire a mass of 500 kilograms, which is over 1,000 pounds. The wire has a diameter of 1 millimeter. Now, that wire may not be able to hold that much weight. It may break. But we're going to leave that to the next video. The maximum stress we can put on a material before it breaks. But right now, let's assume it's not going to break. Doubtful, but we don't care at this point. And we're just going to figure out the change in the length of this wire. Just as it is under compression, tension has the same, you have the same way of solving for that problem, whether or not the object is under compression or under tension. Of course, talking about a wire with a diameter of 1 millimeter, I don't think you can compress that very well. It just kind of bends. But stressing, putting it under tensile stress, that makes a lot more sense. So the definition, again, we have stress divided by strain. And stress, of course, is force divided by cross-sectional area, and strain is equal to the change in the length divided by the original length, and we know that that's equal to Young's modulus. So taking that equation and writing it slightly differently, we can write force divided by area times, because instead of dividing by a fraction, we can multiply by its inverse, so times the original length divided by the change in the length, equals Young's modulus. And since we're looking for the change in the length, I'm going to cross multiply, bring the y over here, bring the delta L over there. So force divided by area times L sub naught divided by Young's modulus equals the change in the length. So reversing the equation, turning it around, we can write delta L is equal to F over A times initial length divided by Young's modulus. And now let's go ahead and plug in the values. What is the force? Well, it turns out if you hang a mass from a wire like that, the force of gravity will be m times g, so we have to have m times g for the force. So that would be a mass of 500 kilograms times a g of 9.8 meters per second squared. The original length was given to us as 4 meters. Divide the whole thing by the cross-sectional area. Now, it looks like it's a wire, has got a round cross-sectional area, circle cross-sectional area, so that would be, the area would be pi r squared. So pi times half the radius, or the radius is half the diameter, 1/2 d, which is equal to 0.0005 meters. Notice that a millimeter is 0.001 meter, but half of that is 0.005 meters. So 0.0005 meters. We have to square that. That's pi r squared for the cross-sectional area. Young's modulus, it being aluminum, it's 7 times 10 to the 10th, 7 times 10 to the 10th newtons per square meter. All right, that will give us a change in length in terms of meters. Let's find out what it is. So 500 times 9.8 times 4 divided by pi divided by 0.0005 squared and times 1 divided by 7e to the 10th equals, and wow, let's see here, that is equal to 0.357 meters. Wow, that would be 35.7 centimeters, which is approximately 14 inches. That's an elongation of 14 inches. I don't think that wire would stay together. 4 meters, of course, is about 13 feet or so. You have a 13-foot long wire, 1 millimeter in diameter, put this much mass on it, it'll probably break, but we'll do that in the next video. What's good enough for us is, if it doesn't break, how long will it stretch? Well, simply put in the force divided by cross-sectional area, pi r squared. Put in the original length, divided by Young's modulus, we get from the table. Crank the calculator, 35.7 centimeters, about that much. So yeah, you do have to take that into account in certain circumstances. It's a good example.
அப்போ மெதுவாக ப்ராப்ளத்துல என்ன போடுறோம்னாக்க யங்ஸ் மாடுலஸ்ல சேஞ்ச் இன் லெங்த் இன்க்ரீஸ் இன் லெங்த் எவ்வளவுன்னு கால்குலேட் பண்ணிட்டே போறோம். மெதுவா அவர் எங்க கூட்டிட்டு போறாருனாக்க பிரேக்கிங் ஸ்ட்ரெஸ் நோக்கி கூட்டிட்டு போறாரு. அப்போ ஒரு மெட்டீரியலை எலாங்குவேட் பண்ணா எலாஸ்டிக் லிமிட் முடிக்க எலாங்குவேட் ஆகும். அதுக்கப்புறம் என்ன ஆகும், தானா தன்னுடைய லெங்த் அதிகரிச்சுட்டு பிரேக்கிங் ஸ்ட்ரெஸ்ஸுக்கு போயிடும். சரி, அடுத்த பகுதிக்கு போலாம்.
We're going to do. In our previous example of Young's modulus, we had a wire just like this. Matter of fact, it's the exact same drawing. Here's a 4-meter long wire made out of aluminum. It has a diameter 1 millimeter, which makes it a radius of 0.0005 meters. And we were going to put a mass of 500 kilograms on that, and we calculated the change in the length. Although I did have a suspicion that the wire was probably not strong enough to withstand that. Because every material has what we would call a maximum stress. And for aluminum, the maximum stress is 2.2 times 10 to the 8 pascals, or newtons per square meter. So, let's see if the stress that this mass would put on this wire exceeds the maximum stress. If it does, the wire will break. So let's calculate the stress in this situation. So the stress is equal to the force divided by the cross-sectional area. So in this case, the force was the weight of this. That would be mg divided by the cross-sectional area. And of course, cross-sectional area would be equal to pi r squared. So mg divided by pi r squared will give us the stress caused by this mass. We have 500 kilograms times the acceleration due to gravity. So that gives us the weight times, divided by pi times the radius squared, and the radius in meters, 0.0005 meters squared. And that will give us the stress caused by hanging a weight on that wire. Again, stress is a function of both the force and the cross-sectional area. A very small cross-sectional area will give us a really big stress, just like a very large force will give us a really big stress. In this case, it's the cross-sectional area that determines that large stress on this wire. So 500 times 9.8 divided by pi and divided by 0.0005 squared equals, so this is equal to 6.2 times 10 to the 9th. And of course, stress is force per unit area, which is newtons per square meter. So that's how much stress that mass hanging from that wire would exhibit itself on the wire. Now, what is the maximum stress aluminum can handle? 2.2 times 10 to the 8. Well, 6.2 is almost 30 times as much, so no question that wire will break long before you have the full weight of this mass pulling down on the wire. The wire cannot withstand that strength. So another question may be, knowing what the maximum stress is, what is the largest mass that we can put here before it will break? So the second part of the question may be, what is the mass max we can put on this wire? All right, so now what we're going to do is we're going to change it like this. We're going to say stress max is equal to F max divided by the cross-sectional area. And F max, of course, will be m times g, which that means that the mass will be limited. So we can say that stress max is equal to m max times g divided by the cross-sectional area, which is pi r squared. And so what we're looking for here is we're looking for the maximum mass. So let's rearrange the equation. So we have m max is equal to, on the other side of the equation, the stress max. Notice that the pi will come up here and go to the numerator on the other side of the equation. The r squared will go to the other side, to the numerator on the other side. And then the g will go to the denominator on the other side, like so. And that will give us the maximum mass, or the biggest object that we can hang from that wire before the wire will break. All right, we have the maximum stress, which is 2.2 times 10 to the 8 pascals, which is newtons per square meter. That's a large amount of force per square meter you can apply to aluminum before it breaks. Multiply times pi multiply times the radius, 0.0005 meters squared, and then divide the whole thing by g, which is 9.8 meters per second squared. All right, so how big of an object can we hang from that wire? 2.2 e to the 8 times pi times 0.0005 squared divided by 9.8 equals, and it says 17.6 kilograms, which is slightly less than 40 pounds. So you have a wire made out of aluminum with a diameter of 1 millimeter, which is not very big. Do not hang more than about 40 pounds or about 17.6 pounds on it, or the wire will break.
ஆகவே இப்ப என்ன பார்க்கிறோம் அப்படின்னாக்க ஒரு ஒயர் அலுமினியம் ஒயர் எவ்வளவு ஸ்ட்ரெஸ் தாங்கும் அப்படின்னு பார்க்கிறோம். நம்ம ஒரு 500 கிலோ லோடு அந்த ஒயர் மேல போட்டாக்க எவ்வளவு ஸ்ட்ரெஸ் வருதுன்னு பார்க்கிறோம். ரெண்டு ஸ்ட்ரெஸ்ஸையும் கம்பேர் பண்ணி இதை காட்டில அது அதிகமா இருந்ததுன்னா ஒயர் பிரேக் ஆகும்ன்ற ஒரு கன்ஃபர்மேஷனுக்கு வரோம். ரெண்டாவது கேஸ் என்னன்னாக்க இந்த ஸ்ட்ரெஸ் மேக்சிமம் கொண்ட ஒயர்ல எவ்வளவு லோட் பண்ணலாம்னு பார்த்தாக்க அந்த லோட நம்மளால கண்டுபிடிக்க முடியும். ஆகவே மிக மிக முக்கியமாக ப்ராப்ளம் டைப் அனலைஸ் பண்ணிட்டு போறோம்.
In our previous here we're going to talk a little bit more about maximum stress, or what we call the breaking stress of materials as it relates to cables. So we're going to talk a little bit about cables as well. Now, what does that mean, breaking stress? Well, here we have a couple of examples. For aluminum, the breaking stress is 2.2 times 10 to the 8 pascals. For steel, the maximum stress or the breaking stress is anywhere from 5 to 20 times 10 to the 8 pascals. And of course, steel is a mixture of metals that we alloy together, and so there'll be different properties for different reasons. And so let's say we have some steel that has a maximum stress of 15 times 10 to the 8 newtons per square meter. Well, that may still not mean anything to us. What does that really mean, the breaking stress, and what does that mean, 2.2 times 10 to the 8 or 15 times 10 to the 8 newtons per square meter? Well, what that means is, let's say we had a really big cable. Let's say we had a really huge cable in such a way that the cross-sectional area was equal to 1 meter squared. Now, of course, that would be a humongous cable. Typically, we don't make them like that because that would be much too difficult to maneuver. If you want to make a big cable, what we tend to do is make a small cable and then intertwine them, make a whole bunch of cables bundled together, make cable bundles, which are much more pliable. They can bend a lot easier, we can work with them a lot easier, and they give us an equivalent amount of strength if we put enough of them together. But let's say for a moment that we had a big cable like this that had a cross-section area of 1 square meter, and we're going to go ahead and apply a certain amount of force to that cable. We pull on the cable, so the cable, of course, that big, would be pretty strong, but it would break anyway if we exceed the maximum stress. And so if we then unitize the cross-section area to 1 square meter, the maximum force that we can apply would be 15 times 10 to the 8 newtons, because it's defined by per square meter. So if this exceeds 15 times 10 to the 8 newtons, then the cable would break, and whatever you hang from the cable would then fall down. Okay, so now typically we don't have big cables like that. We have tiny little cables like this with much smaller radii. Let's say we have a cable here with radius of 1 millimeter. That means a diameter of about 2 millimeters. Let's say it's made out of steel. And we want to know how much force we can apply to that. Of course, remember, force is then equated to how much weight you can hang from the cable. And weight is the mass times acceleration due to gravity. So we want to find the maximum force, and then of course the maximum mass we can hang from the cable. Now, we just have to go do a proportionality. For a cable this big, we can hang this much force on it. So for a cable this small, we can hang this much force on it. This is basically the proportionality of the cross-sectional area, what it really comes down to. So the definition again for stress is equal to force divided by the unit area. And so if we then want to find out what force is, and we want to make this into stress max and then force max, and when that's what we're trying to find, right? We're trying to find the maximum force. We just have to rearrange the equation. Maximum force is equal to the maximum stress, and then times the cross-sectional area simply by multiplying the A with the stress, the cross-sectional area. All right, cross-sectional area, of course, for a cable is equal to pi r squared. So I have to multiply this times pi and the radius squared, and the radius was given to us as 1 millimeter. All right, let's plug in the numbers, see what we get. For steel, the maximum stress was 15 times 10 to the 8 newtons per square meter. We have to multiply that times pi and times the radius squared. That would be 0.001 meters squared. I'm drawing a little bit into the drawing here, made it a little big. Notice a millimeter is 1/1000 of a meter. So we square that, and now we need a calculator. 15 e to the 8 times pi times 0.001 squared equals, and that gives us a force of 4,712 newtons. Now, of course, most of us don't really quite understand what that is unless we deal with those units on a daily basis. So let's convert that to how much mass we can hang from it. And since you know, of course, this is force max. And since we know that the force of an object hanging from a cable is equivalent to the weight of the cable, mg, that means that m is equal to the force divided by g, or in this case, 4,712 newtons divided by 9.8. That would be meters per second squared. And that will give us kilograms, of course. So divided by 9.8 equals, that gives us 481 kilograms. So that would be the maximum mass we can hang from that cable before it breaks. Of course, convert that to pounds. The rough conversion from kilograms to pounds is about 2.2. So if we multiply it times 2.2, we get 1,058 pounds. 1,058 pounds. Now, of course, pounds is a force, kilograms is a mass, but we tend to use those interchangeably when we go from kilograms to pounds. All right, so that would be the maximum weight. So how do you make a really strong cable that has an equivalent strength of a cable like this? Well, what you do is you take a whole bunch of these small cables and you bundle them together. Let's say if you make a bundle of 10 of these, there we go, and you bundle them all together like that. Now you have a cable that is 10 times as strong as its individual strands of the cable. So if each cable can hold about 1,000 pounds, and now you make an intertwining strand, and if you look at it carefully, they tend to be kind of intertwined to each other. Like that, they kind of are rolled over each other, so they're bundled together like that. So if you have 10 strands, that would be 10 times as strong. So that cable could hold 10,000 pounds. Now let's say you take these bundles, you take 10 of those bundles and you bundle them together. So you tend to kind of intertwine them over one another like that. And each one of those bundles has 10 cables as well. And let's say you have 10 of those bundles all, I think you get the picture here when you start intertwining these cables all around each other. Now you have 10 of those bundles. If each bundle can hold 10,000 pounds, then 10 of those bundles can hold 100,000 pounds. And pretty soon you realize you can make some really strong cables by just bundling many of these small little wires together. So basically the single strand like that would be kind of a single wire. You bundle them together, you bundle bundles, and sometimes they bundle those bundles into even much more massive and bigger cables that can hold millions of pounds. So that's how we work with the breaking stress. And obviously it's a lot easier to make cables like this and deal with them than make a big cable like that. That would be kind of hard to do. All right, there gives you hopefully a pretty good understanding of what we mean by breaking stress.
Stress na strain na stress ku strain kulla relation vachittu அதிகமான ஸ்ட்ரெஸ் குறைவான ஸ்ட்ரெஸ்ஸா மாத்துறதுக்கு ஏரியான்ற ஒரு ஃபேக்டர் இருக்கு. அந்த ஸ்ட்ரெஸ்ஸை குறைச்சிட்டாக்க ஸ்ட்ரெயின் ஆட்டோமேட்டிக்கா குறையும். இந்த கான்செப்டை வச்சுட்டு ஐபீம் ஒர்க் பண்றதையும் போன் ஒர்க் பண்றதையும் கான்செப்சுவலா சொன்னோம். சேஞ்ச் இன் லெங்த்தை கண்டுபிடிச்சோம், பெர்சன்டேஜ் ஆஃப் சேஞ்ச் இன் லெங்த்தை கண்டுபிடிச்சோம். அதை வச்சுட்டு பிரேக்கிங் ஸ்ட்ரெஸ் எவ்வளவு மாசம் சஸ்பெண்ட் பண்ணலாம், எதனால மிகப்பெரிய லோட தாங்கக்கூடிய ஒயர் எல்லாம் ட்விஸ்டட் ஒயராகவும் சின்ன சின்ன ஒயர்களுடைய தொகுப்பாகவும் இருக்குன்றத கான்செப்டுவலா பார்த்தோம். இப்ப யங்ஸ் மாடுலஸுக்கான ப்ராப்ளம் ஏரியாவை நம்ம முடிச்சுக்கிறோம். இப்ப அடுத்துக்கு போறோம். இப்போ shear stress இத பாருங்க.
Here we're going to talk about shear stress and strain in our next video. So we're just going to talk about the basics and explain what that really is. Again, when we talk about stress and strain, the definition of the ratio stress divided by strain In this case, it's going to be equal to what we call the shear modulus. So let's write that down. Shear modulus, which is the measurement of the property of a material related to the shear stress and the shear strain. We don't know yet what it is, but hang with me. Again, shear stress is force divided by area, so that hasn't changed. What do we call the shear strain? Well, to illustrate that, I have a little drawing right here. Let's say we have a big block of some sort of material. Let's say that we anchor one part of it down on the ground like here. We nail like a 2x4 down here so that this can't move. And now we go ahead and push on the material in this direction. Well, what will happen is this material will deform. And how it will deform is that this top portion of it will be pushed to the right, and because the bottom portion here cannot move, it'll stay in place. And what we find is that this will deform like this, and the material will, in a way, bend kind of like this. I'm hoping that becomes clear. My drawing skills aren't the greatest, but you can see that the top portion of the material has moved over a distance like this, and let's call this distance, let's say, call it delta x. A certain amount of deformation of the top portion of material where the bottom portion of material is not deformed at all. And of course, it does depend upon the height, h here. If this height is very small, then delta x will probably be very small as well. If h is very large, then delta x could be proportionally much larger as well. And of course, the amount that the material deforms like that will depend upon what we call the shear modulus, which is the strength of the material in this particular fashion. So therefore, the shear strain cannot be defined as, you've probably guessed it, the amount of deformation in this direction right here as a function of the height of the material. So this will be delta x divided by h. And this here is the ratio of shear stress divided by shear strain, which is defined by the strength of the material as being called the shear modulus. So we're going to call this equal to S. And that's simply the ratio of the shear, and I'll write it down again, shear stress divided by the shear strain. Now, materials that are really strong, that have a very high shear modulus, you can push on really hard and they will deform just a very small amount. Metals, for example, will probably fall in that category. And even wood, you have a big wood block and you push on it really hard this way and hold it back here, it's not going to deform very much. Now, of course, you have some other material like a soft plastic or a foam or something like that. You push on like this and it will deform quite a bit. So those have very small shear modulus. Notice that F divided by A, if that ratio is very large, so if that's a really large force divided by a small area, then you expect a large deformation. Unless, of course, the material is really strong. If the material is really strong, then it requires an enormous amount of force to cause a small deformation. So that's really a good way to look at it. Another thing that's different about the area is that the cross-sectional area is the top portion of it, is the surface on the top. And so sometimes it's really hard to visualize. So let me show you some examples where in industry, this is really an important factor. So let's say we have a steel plate that looks like this. Very large steel plate, and it's not very thick. And let's say we want to come with a big machine and cut a piece off. So let's say we have a big machine like this, and want to apply a lot of force in a downward direction and lop a piece off. So cut this little piece off like that, so we end up with a piece taken off that looks like this. Now, of course, how easy is it to do that? Well, that depends on the shear modulus of the material. If this is a very strong material, you need to apply a lot of force. But how does the delta x and the h and all that how is that taken into account? Well, notice that if you look at the other side where the material is being cut off, like so, then you can see that this here becomes the cross-sectional area of the material that's sheared. Notice that what you're going to do is, when this is still attached, you're trying to push this material away from this material, so you're going to try to stress it in this direction. So it's basically stressing it like that, and so the cross-sectional area is simply the cut-up area, or the cross-sectional area of the cut becomes the area here. So the important part of an industrial application like this is to just understand how much force will be required to go ahead and cut a piece of material off. And so what we're looking at here is the limit of that material, and that's usually defined by the maximum shear stress it can withstand. So in this case, we're looking for the shear stress max that the material can withstand, and that's going to be equal to the ratio of the force divided by the area. In this case, the area will be the cross-sectional cut of the material, and the force is the force applied to do that. So once you know the shear stress of the material, you multiply times the cross-section area, and then you can calculate how much force you need to do that. Another application in industry where this is important, if, for example, is where you try to punch out a hole out of the material like this. Let's say you have a metal sheet, and you want to punch a hole in it. So you come with a big punch, and you come down, you apply a certain amount of force, and the question is, how much force does that require in order to punch out that material? Well, when you see the piece that was punched out, you're left with a hole. So let's draw this again over here, and then you're left with a hole, and the hole probably kind of look like this. Not quite. Let me try again. There we go. That's a little better. So that's what the hole would look like. And notice that you have a radius of the hole, and you have a circumference of the hole, where the circumference of the hole is equal to 2 pi times the radius. And then you have the height or the thickness of that material. So it turns out, again, the area that we're interested in, the cross-sectional area that we're interested in, is simply the area left by the side of the hole. So if you say, well, this is the thickness of the material right here, let's call this T for thickness, then the area here would simply be the circumference of the hole, 2 pi r, and you multiply times the thickness T, and that now gives you the cross-sectional area of the cut, which would be kind of the same as the cross-sectional area of the cut here. And again, when you talk about the shear stress of the material, it would be the force required to punch a hole through there, when the leftover area along the sides of that hole would be equal to A, which is equal to the circumference, 2 pi r, times the thickness of the material. And so that's a good application of the shear modulus. In the next couple of videos, I'll do some examples of how we calculate the shear stress and the force required to cut or cut holes through material.
இப்போ shear modulus-னுடைய எக்ஸாம்பிள்ல வந்து நிக்கிறோம். ஒரு பாடி தன்னுடைய ஆரம்ப இருப்பை மாற்றிக்கொள்ளாமல் இணையான விசையினால் தன்னுடைய ஷேப்பை மட்டும் மாத்திக்குது. நல்லா கவனிங்க. இந்த ஷேப்பை மட்டும் மாத்திக்கிறப்ப shear stress force by area தான். ஸ்ட்ரெயின் வந்து டெல்டா எக்ஸ் என்ற ஒரு சேஞ்ச எக்ஸ் என்ற ஹைட் இருக்கக்கூடிய ஒரு பாடி மாத்துச்சுன்னா ஸ்ட்ரெயின் டெல்டா எக்ஸ் பை ஹெச்னு வச்சுட்டு நம்ம ஃபார்முலா சொல்லிடுறோம். ஆனா அவர் என்ன சொல்றாரு, மறுபடியும் யங்ஸ் மாடுலஸ் எக்ஸசைஸ் மாதிரி போறாரு. shear stress எப்ப மேக்ஸிமம் ஆகும்? மேல இருந்து ஒரு ஆப்ஜெக்ட நேரா ஒரு ஆப்ஜெக்ட் மேல மோதணும்னு வச்சுக்கோங்களேன், அது அந்த ஆப்ஜெக்ட ஓட்ட போடணும் அல்லது துண்டாக்கணும் அப்படின்னாக்க இந்த பரப்புக்கு எவ்வளவு மேக்ஸிமம் ஸ்ட்ரெஸ் கொடுத்தா துண்டாகும்? மிக மிக முக்கியமானதான இதையும் பல்க் மாடுலஸையும் பார்த்துட்டா இந்த பார்ட் முடிஞ்சிடும். மீண்டும் சந்திக்கலாம் அடுத்த பார்ட்ல.